So we would like to introduce the method of integration by substitution. And this will actually be the first lecture out of a set of 2 lectures devoted to substitution. We're going to look at the simpler examples, and then we're going to look at more involved examples in the second lecture. And the principle in general is that every differentiation corresponds to an integration. When I say integration here, I mean an indefinite integration, because whenever you have the function f having as derivative with the function g, then an antiderivative for g is the function f. That's what justifies this general principle. So if you start with the chain rule, then the derivative of f of g of x is f prime of g of x times g prime of x. And that leads to the integration f prime of g of x, the antiderivative of f prime of g of x times g prime of x is f of g of x plus c. Now, as we're going to see, methods of integration, in general do not give us a direct answer for any particular integral. They just give us some other integral that hopefully is going to be simpler than the original one. So here, the way we need to understand this formula is that whenever we have an integral of this form, everything pretty much reduces to finding an antiderivative for f prime. Once we know that the antiderivative of f prime is f, then we can compose it with this function right here, the inner function, and that's the antiderivative. So in some sense, we can package this process by saying that if you have an integral of any function which is composed with some other function, and the derivative of that second function, the inner function, is, in other words, is present, then all we need to do is find an antiderivative for the outer function f. And the way that this is expressed is we really try to hide the function g of x by replacing it by a new variable u. And formally speaking, du ends up being g prime of x dx. And so this ends up being f of u du, which is an explicit way of saying that our focus is on finding an antiderivative for the outer function. That's what this means. Whether we will be able to find an antiderivative for the function f or not, that's a different story. Doesn't mean that every substitution should be successful, and it won't be, but at least this is the kind of opportunity that is afforded to us by means of this process. And we should try to see how this works through an example. And in this example, I might say that everything is offered to us on a plate. So here we choose the inner function to be x squared. And we're very, very lucky to have the derivative of x squared being present in its exact form, so it's 2x. And so this is going to be the integral of e to the u du. And then the antiderivative of e to the u is simply e to the u plus c. And even though we're done, we need one more step. And that one step is to actually replace u by x squared. So this will be e to the x squared plus c. This is simply because the integral was given to us as an integral of x, and when we find the antiderivative, our final answer should contain x and not any other variable. Let's do a very similar example. So please pause the video and try to find this integral using the method that we saw. And if we look back at our treatment of the indefinite integral, we will realize that several hints were given about how this can be done in the case of the without having to go through the method that we just explained. However, the method that we just explained formalizes the whole process and allows us to do even much more. So let's see what we will have here. So we will set u to be equal to x cubed. Du will be equal to 3x squared dx. And so here's our du. So this will become cosine of u du. The antiderivative of cosine is sine. And so this will be, we have to go back to our original variable, and this will be sine of x cubed plus c. And this is actually quite ideal, quite convenient, I should say, but one needs to realize that sometimes things are not going to be offered in such an ideal way. And we may actually have to do a little more. And here's how. Let's take a look at the following example. So we have 2 to the x cubed times x squared dx. So here again, we may choose to actually designate x cubed as our inner function, the one that is going to get substituted, except that du is going to be 3x squared dx. So now if we ask ourselves, do we have the full 3x squared here? The answer is no. And there are two ways to remedy this situation. The first way is to actually go back to the integral and multiply and divide by 3 so that the 3x squared is formed. There is another way which is a little more economical, and this is to solve for the part that is actually existent there. And this will give us x squared dx is equal to 1/3 du. So now this will become 2 to the u times 1/3 du. The 1/3 can go outside, and this will be 1/3 2 to the u over ln2 plus c. Again, we should go back to our original variable, which is 1/3 ln2 2 to the x cubed plus c. Now, let's do another example. Let's find the antiderivative of tangent. Find the antiderivative of tangent. We need to write it as sine over cosine. And once we do that, we can set u to be cosine of x. And then du is going to be negative sine x dx. And of course, we don't have that negative sign, so we solve for sine x dx, which is precisely what we have. And let's put it like this, -1 du, because now this is going to be the -1 du. The -1 can always go in front, and I'm putting the du here. And cosine x is u. So this is -1 times ln of absolute value of u plus c. The -1 can go inside the ln. So this will be, and this is quite traditional to do it this way. So this is ln of u to the -1 plus c. Go back to your original variable and you will have ln of 1 over cosine x plus c. And this is nothing else but ln of absolute value of secant x plus c. You might argue that this was already enough, the way it was given here, but people do like to think of the antiderivative of tangent as ln of absolute value of secant. Let's look at a different example now. So imagine that you have an integral that looks like this. And here the idea is that if the 2x plus 1 was outside the root and you had the x inside the root, that would have been much simpler, because we could have multiplied out and we would have got powers of x. So what we do is we set u to be 2x plus 1, and du is going to be 2 times dx, or dx is going to be 1/2 times du. Here there is an additional step, because once we try to perform a substitution, we have this x right here. So we need to also solve for x, and this will give us u minus 1 over 2 being equal to x. So now we have all the pieces together. And so x is u minus 1 over 2. Square root of 2x plus 1 becomes square root of u. And dx is 1/2 du. So I can take the 1/2 and 1/2 outside. This is 1/4. And we have to be careful here to put a parenthesis, because the fact that it was all given as 1 was part of the fraction that we had there. And now this is where we explain how it would have been easier if the square root was had u in it, or had simply x in it from the very beginning. Because the idea here is that you can multiply this out, and this will give us u square root of u minus square root of u du, and this can become just powers of u. So this is u times u to the 1/2, meaning u to the 3/2, minus u to the 1/2. And finally, now we can find antiderivative. So this will be 1/4. The antiderivative of u to the 3/2 is u to 3/2 plus 1, which is u to 5/2, divided by 5/2. Dividing by 5/2 is the same thing as multiplying by 2/5. And the antiderivative of u to the 1/2 is found in a very similar way, meaning we take 1/2 and we add 1 to it. So that gives us u to the 3/2 on the top. And we have to divide by 3/2, which is the same thing as multiplying by 2/3 plus c. And if we like, we can multiply out by 1/4. So this will give us 1/10, and u should be replaced by 2x plus 1, going back to the original variable. And minus 1/4 minus 2/3 is minus 1/6, 2x plus 1 to the 3/2 plus c. And obviously, this is a much, much more interesting example than the one that we could have seen. This is the most complicated integration that we have done so far. The way we should be thinking about these examples is not whether we would have thought to do it this way, but rather, now that we have seen it, let's do it many times. Let's get used to it, so that if we see something similar next time, we will be able to actually do it ourselves. And that's all. Okay. Thanks for watching.